Okay, this is going to be the video for section 2.4 for differential equations on solving what are called first order exact equations. So another type of equation. I would say this procedure isn't used as frequently as the other two that we learned, but another one to have on our toolkit that we can pull out if needed. Let's say we have a differential equation of this form and we go about getting ready to solve it like we're separating the variables. So we have dy dx equals negative y over x. If we multiply both sides by dx, we get dy is negative y over x dx. And then we move this y to the other side. Let's say we've got this, we've got dy 1 over y equals negative 1 over x dx, right? We could integrate that with natural logs and go separation, but there's another way we could go, and that is I could multiply both sides by the opposites to not separate the variables, but let's multiply both sides by x and y here to get x dy equals negative y dx, and then bring everything onto the same side. Now, if I did that, I would get y dx plus x dy equals 0. It's just another way to rearrange that rather than getting the variables separated on each side. In this case, I've got y dx plus x dy equals 0. Okay, so this is a special form. If you can take an equation and rearrange it into this particular form, it's called an exact equation, okay? Or at least it could be an exact equation. There's another condition. So if you rearrange it like this, what we do is you have a dx term, a dy term, and then it's specifically a 0 on the right-hand side. Whatever this function is, we label m, and whatever this function is here, we label n. And so it turns out that if you can write a differential equation in this form where you have an m function times dx plus an n function times dy equals 0, these functions can be functions of a mixture of x's and y's. And it's also true that the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. Then the differential equation is called an exact equation. I think the reason why I haven't seen this used as frequently is just that not that many equations are in this form, but when they are, you can use this interesting procedure to solve. Okay, and again, I've derived the steps that I'm going to show you here next in a separate PDF if you're interested in the theory as to why it works. But we're going to use a procedure to solve this, which is remarkably similar to what we did in Calc 3 when we found a potential function for a conservative vector field. Remember, we had a way to kind of postulate a solution f by making its x derivative equal to something, and then you had a function of g, a function of y, and then you made that equal to the derivative of y, and then we kind of solve a solution that way. So this is sort of an analog to that. It reminds me a lot of that same procedure. Here's the procedure. If we have a first order exact differential equation, right, we first want to put it in that form with x dx and dy terms separated. Verify that it is exact by checking that the partial derivative of this with respect to this variable is equal to the partial derivative of this with respect to this variable. And then we go ahead and postulate that there is a solution of the form f, which could be a function of both x and y, but it's equal to a constant c, a numerical constant. And we initially set fx equal to the m term, just like we used to set fx equal for a potential function equal to the x component of a field. Then we integrate both sides with respect to x, and that produces an integral here, a term, right, plus an integration constant, but that integration constant could be a function of y since we're doing a partial derivative with respect to x. So we write this as g as a function of y. Then we take the partial derivative of all of this with respect to y to find fy, and we force that to be equal to the n, the dy component of this. And then we take the antiderivative and solve for g prime. And then when we finally take the antiderivative of the g prime to find g, we can fill that back into the f that we had, and that will give us a solution. Now, at the end, people mistakenly think that that equation we get is the solution, but that's not true. It's what we get equal to a constant is the solution. And then we can establish that constant by setting initial conditions if we have them. Easiest to see this with an example, I think, but you're going to see how similar this is to to the potential function procedure we had in last semester. So let's say we have this differential equation, really crazy looking hard differential equation. Okay, first we're going to put this in differential form by cross multiplying and then gathering terms. So you can carefully rearrange this into this form. This times dx plus this times dy equals 0. We're going to make sure that this is a differential equation or an exact equation. This is m, this is n. So we're going to take the partial derivative of all of this with respect to y, right? So the partial derivative of this term with respect to y would be 2 times e to the 2y. And this term here has two terms or two functions that are multiplied. So we'll need to do product rule, first times derivative of the second plus second times derivative of the first. So this is y times negative sine of xy times the partial derivative of the inside with respect to y, which is x. And then cosine xy times the partial derivative of y with respect to y, which is 1. And so that ends up being this. And then when you take this side and you take the derivative of this with respect to x, then you get this derivative is 1 times 2 e to the 2y as a constant. And then this requires product rule. So you've got first times derivative of the second plus second times derivative of the first, which ends up being x times the derivative of this is negative y sine xy plus cosine xy times the partial derivative of x with respect to x is 1. And then this term out here has no x's, so its partial derivative with respect to x is 0. And sure enough, those two things match, which means this is an exact equation. And that means it qualifies for the procedure we're going to do next. Okay, so now that we have m and n identified, what we're going to do is we're going to say f, the solution we're after, equals a constant, right? Where we're going to find this function is first set fx equal to m, e to the 2y minus y cosine xy. And then we will find f by taking the antiderivative with respect to x of both sides. So we have to take the antiderivative of that with respect to x. This term, this is a constant, so the antiderivative is just that constant times x. And over here, we're going to have to, let's see, the y is just a constant, but we have cosine of this. So essentially we have something where it's cosine of a function of y here. So there's an inside function. So I am going to do a u substitution. U is xy, so du is y times dx, because y is considered a constant while we're doing this. X is the variable. And so this ends up being the same as the integral of cosine of u, which is negative sine of u, so it's negative sine of xy. So we had to do some fancy integration with substitution. But we found that f, which was the integral of the m part, is this plus an integration constant. But this integration constant could be a function of y, just like it was in the potential function. So the next step is we're going to have to take the partial derivative of all of this with respect to y, both sides, and then force that to be equal to the n. So we'll take the partial derivative of the result with respect to y. So the partial derivative here is the x stays there as a constant. The derivative here is e to the 2y times the derivative of the inside, which is 2. Right? This would be the derivative of sine is cosine, but times the derivative of the inside, partial derivative with respect to y is x. So we have x cosine xy. And then this we're just going to call g prime of y, where we recognize that the variable of differentiation is y. All right, so that is what fy is equal to, right? So that must be set equal to the y component of this. So we set that equal. So all of that has to equal this. And then we match things up. It looks like these match exactly. And so what's left over for g prime of y is 2y. So g prime of y is 2y. And therefore, to find g, we just take the antiderivative with respect to y of that, and we get y squared. So finally, we fill in f. And our f before was x e to the 2y minus sine xy plus gy. Now we fill in gy to get this. Okay, now this is an expression f. That's not the solution. The solution is that equals a constant. So this is how we put the integration constant for the differential equation in. All right, so that's the procedure that we use for exact equations. You can kind of see why it might be necessary, right? Because there's no really way we could have separated that right-hand side to do separable variables, and it's definitely not a linear equation. There are nonlinear terms here with either with e's, but we're using the y variable. So yeah, definitely need a new solution method for that. Okay, we can try this one too. This was all the procedures here. So you can pause the screen. Here's the procedures. Give this a try. And then I'm going to go ahead and erase this part um, and solve it for you. So pause the video and then try it and then unpause. See if you get what I get. All right, we've got, this is already in the form that we need. So we need to check to see whether or not this is m, this is n. So we need to see whether dm dy is equal to dn dx. Is this true? So what's dm dy? So the partial derivative of this with respect to y is 2x. And what is dn dx? That's also 2x. So yeah, this is exact. So we can proceed. So what we're going to do is we're going to say there's some function f where fx is equal to the m field. So that's going to be 2xy. And then to get f, I'm going to take the antiderivative of both sides with respect to x to undo this fx. That will give me my first copy of the f function. So taking the antiderivative, treating x as the variable, means that this is going to become, we've got a 2 and a y here as a constant. The derivative of x is 1/2 x squared, antiderivative, plus a constant. Okay, but these cancel, so I'm going to write this way as f equals y x squared. And this could be a function of y, so I'm going to write that as gy. Then I will take the partial derivative of that with respect to y on both sides. And what I will get is, on this side, it's fy. And on this side, this is 1 times x squared as a constant plus g prime of y. And we're going to force that now to be equal to the y component of this differential equation. So as I'm matching these terms, it looks like this and this cancel. So what's left for g prime is that g prime of y has to equal -1. Okay, so to find g, we're going to take the antiderivative with respect to y sides. And that will give me what g is. G of y is the antiderivative of -1 dy, so that's going to be -y. Okay, and so now when I plug this into my version of the equation here, I had that f was yx squared plus gy, but gy is -y. And I can now say that the final solution is this right here has to equal some integration constant. Or if you wanted to, this is an implicit solution, we could solve this for y by factoring it out and getting x squared minus 1 equals c, and say that y is therefore c over x squared minus 1. This is an explicit form solution. Still general because we haven't established the constant. All right. Okay, let's do another one, and I'll show you another thing that you can do here if you want. Here's another problem. Let's put this in the right form. You can pause this and try it, and then unpause. Just got a couple more examples for you here. So if I multiply both sides here, I would get y1 minus x squared dy equals y squared minus cosine x sine x dx. So if I move this over to the other side, maybe I could write it like this. I could say, actually, let me move this to the other side and make it negative by swapping these terms, right? If I reverse these terms, I get the negative. And then when I move it to the other side, it'll become positive. So just to try to avoid negatives as much as possible, if I do that? And then I have y1 minus x squared dy equals 0, which makes this m and this n. Let's check to see if it's exact. What is dm dx? That's going to require some, well, let's see, with respect to x. So we'd have to do, I'm sorry, it's dm with respect to y. Yeah, we have to do this with respect to this variable. So what is dm with respect to y? Well, this whole thing has no y, so it's 0. And this right here is going to be, the derivative here is 2y, so it's going to be minus 2xy, right? So negative 2xy, right? And dn with respect to x, so this one with respect to x is, let's multiply that out actually. It's y minus yx squared. So there's no x here, but here this would be negative 2xy also. So yeah, this is exact. And that means we can start by setting an equation equal to something. Now, normally we would do this, fx equals this, but that's going to require integrating this right away, which this is crazy to try to integrate. So we're going to try something else. There's no reason why we can't start with this one. You don't have to start with x. It's just that we have to end up with fy has to equal this and fxx equal this. So if you have an easier term in the y, start with the y. And then you would say, okay, fy has got to equal y minus x squared. Okay. Therefore, if I take the antiderivative with respect to y now, on the left-hand side, I'll be left with my first copy of f. And this 1 minus x squared just becomes a constant. So it's 1 minus x squared. And then the antiderivative here is 1/2 y squared, plus an integration constant, which could be a function of the other variable, which is x in this case, because we started with fy. Right? The next thing I would do then is take the partial derivative of this time with respect to the other variable, which is x. So now I'm going to get fx. And so here, let's see, this 1/2 and this y squared are just a constant while I'm dealing with x. But what is this right here? The partial derivative, well, you know what? Let me multiply this out. So this is really 1/2 y squared minus 1/2 y squared x squared plus g. So I just feel more comfortable without dealing with the parentheses in there. Too many assumptions about properties. Okay, the derivative here with respect to x is 0. The derivative here with respect to x is this 2, which cancels this. So it's negative y squared x. And then plus g prime of x, where we understand that this derivative is with respect to x. We're going to force that to equal the m term, which is cosine x sine x minus xy squared. Okay, so when I look at that, it looks like negative xy squared is on both sides, which leaves g prime to be cosine sine. Okay, so yeah, I didn't get completely away from having to do an integral here, because if g prime of x is equal to cosine x sine x, then we could get g from taking the antiderivative of that. That's not going to be too bad though, because if I do a u substitution and I pick that u is sine of x, then du dx would be cosine of x, and therefore du would be, du would be cosine of x dx. So that means this can be rewritten. This is the u, and the cosine x dx is the du, right? And so this is just going to be 1/2 u squared, which therefore means 1/2 sine squared of x. And so my g of x is that. And that means my original f function is going to be, I had a copy of it up here. It was 1 minus x squared times y squared times 1/2, right? Right here, times 1/2. And then I have to add on the g of x, which I now know is 1/2 sine squared of x, okay? And so the final solution is that equals a constant. This is the implicit solution. And if you wanted to come up with the general solution, the particular solution, we have to use the initial condition. When x is 0, y is 2. So let's do that. When x is 0, y is 2. So if I plug in 0 for all x's and 2 for all y's, then I'm going to get 1/2 1 minus, let's say x is 0, so that's 0 squared times 2 squared plus 1/2 sine squared of 0 equals the constant. So this is going to be 4 divided by 2 is 2 times 1 is 2 plus sine of 0 is 0. So that means c is 2, and that means that our particular solution is 1/2 1 minus x squared y squared plus 1/2 sine squared x equals 2. Now that's an implicit solution. If you wanted to, you could solve it for y. Um, I don't. I'm not going to bother to do that, but yeah, you could do things like multiply everything by 2, so you get 1 minus x squared y squared plus sine squared x equals 4. You could move this term to the other side and divide, and then take the square root. But let's just leave it in one of these forms. Okay. All right, and one last example to wrap this up. Sometimes you can use an integrating factor to turn a differential equation into an exact equation. Now this one is a little trickier and derived in the book, and I believe I don't know if I put this in a PDF or not, but if an equation is in a differential form, but that's not exact, so you go through the rearrangement process and you find that these partial derivatives are not equal, then you can identify m and n in the form of the following two quotients with partial derivatives. So you take the partial derivative of this with respect to the x variable and the partial derivative of this with respect to the x variable and divide by n. And then you take the partial derivative of this with this respect to the x variable minus the partial derivative of this with respect to the x variable and divide by m. Algebraically simplify, and if either of these quotients simplifies to a function that's of only one of the variables, then that quotient can be used to compute an integrating factor. Very difficult to show why this is true. But then if you multiply by the original dE by that integrating factor, it will turn this into an exact equation where this relationship is true. This only works in some cases. And it'll only work if when you check these quotients, they produce a function of only one of the variables. This is very, very infrequently used, but just to show you, I've got one example for you here. Let's say that we've got this is already separated, and we're going to try to verify whether this equation is exact. So here's my m, and here's my n, and I want to find my dm dy, right? Well, dm dy would be equal to x, but dn dx would be equal to 4x, right? So those are not equal, so this is not exact, okay? And we can't use the procedure. It's also not separable, and it's also not linear. So none of the procedures work so far, okay? But if we compute these special things here, I think I might have a typo in the notes there that I need to fix. Let me look at something really quick here. Sorry for this delay, but I need to verify something in the... Yeah, there's a typo on this other page. So this is supposed to be, we need to fix this, that it's mx, let's see, it's my minus, all the m's are y's, yeah. So yeah, this should be a y here. Anytime you see the m, it's with respect to y. I'm not sure why, I just think that when I copied that over, that didn't get done correctly. So please make that note, that change in your notes. Okay. So the quotients that we're supposed to check are, now that I've got that corrected, it's supposed to be my minus nx over n and nx minus my over m. Okay, let's check that. So my is what we computed up here. So this is x, and nx is this one, which is 4x, divided by n, which is 2x squared plus 3y squared minus 20. And that ends up being, let's see, negative 3x over 2x squared plus 3y squared minus 20. But if we do the same thing over here, we get nx is 4x minus my, which is x, over m, which is xy. This becomes 3x over xy, 3x over xy, but the x's cancel and we're left with 3 over y. This one here is a function of only y. And what that means is that right there can be the px, actually py, for an integrating factor. So we're going to build an integrating factor from that. Okay. So if I make an integrating factor, e to the integral of p dx, or y in this case, it's going to be integral of 3 over y dy, which is going to be 3 times natural log of y, which is going to be natural log of y cubed, which is going to be y cubed. So we can multiply the original differential equation by y cubed and form a new differential equation that's equivalent. Because if you multiply the whole thing by something, you get the same equation, right? So as long as y isn't 0, if I multiply this equation by y cubed, the whole thing, then I get xy to the 4th dx. And then now we have y cubed here. So this is going to be 2x squared y cubed plus 3y to the 5th minus 20y cubed dy equals 0. And it turns out that this is exact. And then you can use the procedures that we've done. And in fact, let's verify that. This is my new m and my new n. So now dm dx, I'm sorry, dm dy would be 4xy cubed, and dn dx, that would be 4xy cubed, no x's. So now this is exact, which means I can do the procedure on this. Okay, so the procedure is to start with, well, let's start with fx. Fx, that seems to be easier, is xy to the 4th. Therefore, f is going to be the antiderivative of that with respect to x. So that's going to be 1/2 x squared y to the 4th plus our function of the other variable as an integration constant, right? Make sure I'm not introducing any problems here. Yep, okay. And then we'll take the partial derivative of that with respect to y to get that this is, when you do that, that's going to be 2x squared y cubed plus g prime of y. We'll force that to be equal to this component, which is 2x squared y cubed plus 3y to the 5th minus 20y cubed. These cancel, which means that the g prime has to equal what's left, 3y to the 5th minus 20y cubed, right? So then if I find g by taking the antiderivative of this, with respect to y, then I'm going to get 1/2 y to the 6th, right, minus 5y to the 4th, right? Is that right? Yep. And so therefore, my f function is going to be what we had up here, 1/2 x squared y to the 4th plus the g function, which is 1/2 y to the 6th minus y to the 4th equals a constant. So we took something that wasn't exact, used this kind of special form to find an integrating factor to force it to be exact so we could do our procedure. The exact procedure isn't used that often anyway, and this is used even less so, but there's an important typo to correct. It's always this derivative with respect to the other variable, So this m should be my. And then you use whatever that is as the px or py to find the integrating factor. All right, and that's it. That'll wrap up section 2.4.